Manjul Bhargava.
Can you hear me okay? Yeah, okay. Great, well thank you so much. It's a great pleasure and honor to be here finally at the Arizona Winter School. The Winter School actually has a lot of memories for me. I was actually at the very first Arizona Winter School when I was a beginning graduate student. And I essentially came every year when I was a graduate student, all those years after. And it was an awesome experience for me. It didn't used to be as big as it is now. It's grown tremendously since it started, but it was just as intense. Every student was in a student group at the time, and every student group had at most 5 students. There were about 20 students total. So it was a lot smaller, but it was just as intense as it is now. And I met lots of great people during those years and also learned a lot of great mathematics. So I just wanted to begin by expressing my deep appreciation to the organizers and to the visionaries behind this winter school for running such a successful and rewarding program for so many years. So I'm very thankful to you. And I hope it continues running for many more years. So I didn't expect that I'd be on the other side of this so soon. It feels kind of weird being on this side. But as I said, it's a real pleasure and honor to be able to try to give back at least a little bit to this program. That was such a great experience for me. Okay, so enough reminiscing. So what I wanted to talk about in this lecture series is classifying rings. So the Arizona Winter School used to be small enough that we could write on the blackboard. I'm not so used to this. Okay, so I want to talk about classifying rings. What kinds of rings? Well, rings that are sort of finite over Z as a Z module. So we're going to be interested in rings that have finite rank as a Z module. So we're going to talk about rings of rank n. So a ring of rank n So a ring of rank n is well, we're going to assume commutative, associative, with identity, with a multiplicative identity. So you can say with the unit. Ring that's free of finite rank as a Z module. So it looks like Z to the n as an additive group. So it's free of rank n as a Z module. Okay, so it's a ring that's finite over Z of rank n, okay, free of finite. So it looks like Z to the n as a lattice, as an additive group, but it has a ring structure on it. Okay, so a typical example, of course. So an order in a number field, right? So an order in a degree in number field. Right, is a ring of rank n. So that's sort of the prototypical example of a ring of rank n, an order in a number field. In fact, which are the rings of rank n that are orders in number fields? It's exactly the integral domains, right? Because if you have a ring of rank n that's an integral domain, then you can take its fraction field, and that will be a finite extension of the rational numbers. So if one understands rings of rank n, then one can restrict to the integral domains, and those will correspond to the orders in number fields. Right? Is it okay if I write smaller? Yeah, because I'm not able to fit very much on the page right now. Okay. So the question I want to address is how can one classify? So we have to make precise what we mean by classify, but how can one classify the rings? So, I mean, given n, how can one classify the rings of rank n? Okay, so that's the question. So what we'll do is we'll just start doing it. So okay, let's start with the simplest possible case. I guess that would be, well, n equals 2. Well, okay, n equals 1. Okay, so n equals 1 means you have your additive group is Z and you need a ring structure on it. Well, it's going to be Z. Okay, so there's only one ring. Okay, so theorem 1. There's only one ring of rank 1, namely Z. Okay, so that's pretty easy. Okay, actually n equals 2 is not that much harder. So what does it mean to be a ring of rank 2? Well, okay, it's a ring with identity, so you can always take your first basis element. So if you take a basis of your ring, you can call one of them 1, which is the identity. So any ring of rank 2, which we're going to call quadratic rings. Oops, quadratic. So quadratic ring means ring of rank 2. Any quadratic ring has a basis. Say 1 and tau. Okay. So we choose our first basis element to be the identity of the ring. The other guy can be tau. So let's call this ring S, say. Okay, so we choose such a basis of the ring. And to specify the ring structure on S, what do you need to know? Well, you need to know how to multiply the basis elements. But of course, 1 times 1 is going to be 1. 1 times tau is going to be tau. So the only thing you need to know to specify ring structure on S is tau times tau. Right? So to specify the ring structure, all you need to know tau times tau. So tau times tau is of course going to be an integer linear combination of 1 and tau. Right? So tau times tau is going to be b times tau plus c. Right, for some integers b and c, right? Oops, let me see. B and c are integers. Now, of course, tau is not uniquely determined. Tau can be translated by any integer, and it would still be a basis, right? It would still form a basis. So we might as well translate tau. So you can translate tau by some integer. And what happens when you translate tau by an integer? What happens to b? Right? So if you translate tau by an integer, say a, right, then b is going to change by 2a. Right? So in other words, you can translate tau by any integer, and that's going to translate b by some even integer. So you can translate tau by an integer so that b translates by any even integer you want. In particular, you can assume that b is 0 or 1. Right. So you can translate tau by some integer so that b can be assumed to be 0 or 1. So we could have picked tau that way. We could have translated tau by something so that b can be assumed to be 0 or 1. Okay. Right, and there's essentially a unique way to do that translation. The other thing one could have done is negate tau, and that doesn't... So in any case, even if you negate tau, you can always translate. There'll be a unique thing that you can translate by so that you get b to be 0 or 1. And that's essentially unique, and so that essentially gives you a unique basis element tau up to this negation issue. So what we find is that quadratic rings then, right, so that sort of gives a canonical representation of your quadratic ring. You said b to be 0, 1, and whatever c you get will specify your quadratic ring. So quadratic rings, right, the set of quadratic rings up to isomorphism, right, are sort of in one-to-one correspondence with two kinds of taus. Either you have this tau squared equals c, or you have tau squared, that's the case b equals 0, or you have tau squared equals tau plus c. And the discriminant of these quadratics in each of these cases, right, what is the discriminant of this quadratic equation tau squared equals c? It's 4c in this case, and it's 4c plus 1 in this case. Right, so this right here, c ranges over z. Okay. So as c ranges over z, we have these two possibilities for the quadratic ring, which lead to two different numbers for this discriminant, either 4c or 4c plus 1. So that's called the discriminant of the ring. And what we're seeing is that quadratic rings are essentially, they're going to be characterized by this discriminant, right? As c varies over all integers, we're going to get either an integer, we're either going to get a discriminant 4c or we're going to get a discriminant 4c plus 1. So quadratic rings are basically in one-to-one correspondence with the set of all integers that are 0 or 1 mod 4. Right, so the set D. So quadratic rings up to isomorphism are in one-to-one correspondence with D, which are the numbers in Z that are 0 or 1 mod 4. Mod 4. And what is the correspondence? Right, so, okay, so I don't know how to do this. Okay. So, okay, so theorem 2. So we have theorem 2 now. So theorem 2 says that quadratic rings, right, rings of rank 2 up to isomorphism, are in one-to-one correspondence with the set of integers that are 0, 1 mod 4, which is this blackboard bold D. And what's the correspondence? If you have a ring S here, what you do is you take this discriminant of the quadratic equation that comes up in defining your ring, and that's called the discriminant of S. One can check that that discriminant of the quadratic doesn't change no matter how you translated B. Okay. So it's an invariant of S. And conversely, if you have some integer D that's 0, 1 mod 4, then you can make a quadratic ring by simply adjoining a tau to Z that satisfies a quadratic with discriminant D. Okay. So there's a uniform, you can do it this way, or you can do it in a uniform way as follows. You adjoin the square root of D like this. So Z adjoin D plus square root of D over 2. You can check that that satisfies a quadratic of discriminant D. Okay.
Then Z would equal 0.
Yeah, so if you adjoin the square root of 0, you get Z bracket x mod x squared. So, and if you join the square root of 1, then you get Z direct sum Z. Okay, so the case D equals 0 corresponds to this degenerate ring, Z bracket x mod x squared. And the case D equals 1 corresponds to a non-integral domain Z direct sum Z. So you can make sense of what you mean by adjoining a square root of 0 or square root of 1. Okay, so rank 2 cases, pretty easy, right? That's okay. Feel bad about moving this. Okay. Is it okay to move? Is that ready? Okay. Okay, so the cases n equals 1 and n equals 2 are pretty easy. In the case n equals 2, we saw that the ring is essentially characterized by the discriminant. Now this discriminant is an invariant of a ring of rank n for any n, actually. Not just for quadratic rings. So So this notion of discriminant, which was so useful in describing quadratic rings, is actually well defined. Is an invariant for any ring of rank n. So how's it defined? So first of all, so it's defined as follows. So suppose you're given an alpha, an element alpha in your ring R that has rank n. Then you can talk about taking alpha and multiplying everything in R, okay? The times alpha map, right? So you have this map times alpha that takes R to R, right? Just multiplying everything by that element alpha, right? Alpha is an element of your ring, so you can multiply everything by alpha, and you get a map from R to R, which is of course a linear transformation. So it's a linear transformation. So it's a linear transformation of R, right? A z-linear transformation, let's see. Right, so R looks like z to the n as an additive group, and times alpha is doing a linear transformation on that z to the n, sending it to z to the n. So you can define, for example, the trace of a linear transformation. So this trace of alpha is going to be defined as just being the trace of the corresponding linear transformation times alpha. So that's how one can talk about the trace. Similarly, one can define a norm, right? The norm of alpha is just defined to be the determinant of that linear transformation, multiplication by alpha. Okay. So in a general ring of rank n, you can talk about traces of elements, you can talk about norms of elements. And in particular, since you have this linear map called the trace from R to Z, right? So the trace takes you from R to Z. You can use that linear map to make a bilinear form. So there's a natural bilinear form R cross R to Z, which takes xy, xy to trace of xy. So just knowing this ring structure on R, you get, and in particular you get this inner product on R, defined by this trace pairing, right? X comma y goes to trace of x times y. So if, say, alpha 0 dot 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 alpha n minus 1 is a basis for R, then this discriminant that we were trying to define, disk of R, that's defined to be just this determinant of this bilinear form, or of that quadratic form. So discriminant of R is just defined to be the determinant of trace of this matrix. So this trace of this matrix, alpha I, alpha j. Oops. I should put it this outside. So you take trace of alpha I, alpha j, and you take that, so as I and j, right, so I and j range over. So you take that matrix, right, so you take trace of alpha I, alpha j, right, you make a matrix of it over all I and j, and you take the determinant, right? So in particular, this is just the determinant of that corresponding quadratic form, right? This trace of x squared. Right, trace of x squared is a quadratic form in n variables on R, and we're just taking the determinant of that quadratic form. That's the discriminant. Yeah, so that's how one defines a discriminant of a ring in general. You take this natural quadratic form on your ring of rank n defined by a trace of x squared, and you take the determinant of that. Yeah, so it's a very natural invariant for any ring of rank n. It's actually the invariant for rings of rank n. In particular, it's the invariant for number fields, right? If you take a number field of degree n, you take its ring of integers, that's a ring of rank n, you can take its discriminant. And that's what you call the discriminant of the number field also. So in a sense, this discriminant sort of measures the size of a number field, or the size of a ring of rank n. Okay, so it's the most fundamental invariant. And what we saw in the case n equals 2 is that this invariant, you can check that this invariant agrees with how we define the discriminant in the quadratic case, just as the discriminant of tau. Okay, these discriminants agree, and what we saw in the rank 2 case is that the discriminant completely characterizes the quadratic ring. But what I want to point out is that it's not, the discriminant was a complete invariant for quadratic rings, but it's not a complete invariant in general. So it's not a complete invariant for n bigger than 2. So, in other words, it's possible to have cubic rings, in other words, rings of rank 3 that have the same discriminant. Okay. So you can use the discriminant invariant to show that cubic rings are not isomorphic, but you can have cubic rings that are not isomorphic that do have the same discriminant. So it doesn't always give you a complete invariant. Okay. Okay. Any questions about the definition of discriminant? Okay. 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 Okay, so I brought that up just to say that the discriminant works in the quadratic case, but you need more information as soon as you go to n equals 3, so as soon as you go to the cubic case. So n equals 3, you need more information than just the discriminant. Discriminant is one invariant, but what completely characterizes cubic rings? So that's theorem 3. So this theorem is due to Dillon and Fadeev. In the case of integral domains, and it was extended by Gann, Gross, and Savin for general cubic rings. This is about 1970 or so. This is about 2000. So what their theorem says is that cubic rings, in other words, rings of rank 3, so cubic rings up to isomorphism, are in one-to-one correspondence, not with their discriminants, but with integral binary cubic forms. Okay, so not quadratic forms. I know this is a quadratic forms conference, but we have to go to cubic forms. But quadratic forms will come back when we go to higher n. So, okay, so they correspond to integral binary cubic forms. Modulo the action of GL2Z. So what is an integral binary cubic form? It's just something that looks like ax cubed plus bx squared y plus cxy squared plus dy cubed. Okay, so it's a homogeneous degree 3 polynomial. So if you can't see those exponents, you can figure them out, right? Because every term has homogeneous degree 3. Okay, and here a, b, c, d are integers. Okay, so that's what it means to be a binary cubic form. So you take all binary cubic forms. GL2Z naturally acts on binary cubic forms just like it acts on binary quadratic forms. Right? You can do linear changes of variable in x and y. Right? Invertible linear changes of variable. Right? So you can replace x by a linear combination of x and y by a linear combination of x and y. And if that linear combination is defined over the integers and is invertible, then it's in GL2Z. So that's how GL2Z acts on binary cubic forms, just by change of variable. And what this Dillon, Fadeev, Gann, Gross, Savin theorem is saying is that the equivalence classes of integral binary cubic forms under this action of changing variable, those equivalence classes are in one-to-one correspondence with isomorphism classes of cubic rings. So how does this work? So, well, let's take any cubic ring. Okay, let R be a cubic ring. And we can take a basis for it. So with basis, say 1, and then we need 2 more things, so we call them omega and theta, due to historical reasons. That's the omega and theta were used by Dillon and Fadeev, and people have used it ever since. So we can choose some basis like this. Okay, and what do we have to say the ring structure on R? We have to decide what omega squared is, what theta squared is, and what omega times theta is. Right? Everything else is multiplication with 1, which we know. So, in particular, omega times theta is going to be a linear combination of 1, omega, and theta. Right? If we translate omega by an integer, right, then we can, in omega times theta, we can get rid of the omega coefficient. Everyone see that? So maybe I'll write this out. So to specify the ring structure on R, we need to know omega squared. So omega squared is going to be some linear combination of 1 and omega and theta, right? And theta squared is going to be some linear combination of 1 and omega and theta. Right, we need to know these blanks. And omega theta is going to be some linear combination of 1 omega and theta. So the first thing to notice is that if you translate omega by an integer, what happens? That changes just the coefficient of theta here, right? And same way, if you translate theta by an integer, that's just going to change the coefficient of omega here. So what we can do is we can translate omega by that integer so that this guy disappears, right? And we can translate theta by that integer so that this coefficient disappears, right? There's a unique way to do that. So by translating omega and theta by suitable integers, you can assume these are 0. What do I mean by these? These. Okay? Okay, so these you can just assume are 0 over here. Okay, and once that's done, then we can assign, let's just assign variables to these. So we'll call this B, we'll call this minus A, we'll call this D, let's call this minus C. Okay, so I assigned values to those, just indeterminates. And once you assign these indeterminates, okay, and we'll call these, say, N, M, and L. Okay. So what happens is, we can use the associative law to figure out relations among these indeterminate coefficients. Okay, this is going to be an associative ring, as we assumed. So we can, in particular, work out, so by equating, say, omega theta times theta with omega times theta squared, right, and omega squared times theta with omega times omega theta, you actually find that N, M, and L, okay, so if you just multiply these out using these relations that we've written down in terms of these indeterminates, you get a bunch of equations involving N, M, L, A, B, C, and D. And what you find is that N, M, and L are uniquely determined by A, B, and C, and D. So by equating these, so it's kind of a fun computation. I won't do it here. Let's try it out. So by equating these, we find that N is equal to minus AC. The associative law in R forces this upon you, that N has to be minus AC in order for the associative law to hold. M has to be minus BD. And L is equal to minus AD. So these relations are just forced upon you by the associative law. If you just write it out, okay, you'll just see that. And A, B, C, and D are free. They can be anything. They can be anything, and then N, M, and L are forced to be this by the associative law, and you get a cubic ring. So in other words, A, B, C, D sort of determine everything about the ring, about the cubic ring, just by writing out the multiplication laws and enforcing associativity. So what do we do? So these A, B, C, D determine everything. So to R, we associate. Remember, we need to get a binary cubic form. Well, here we have our A, B, C, D, 4 coefficients. So to R, we associate the binary cubic form. You can guess which one. So what one checks. So this is a nice association because one checks that changing basis this omega theta of R mod Z to something else, right, by an element of GL2Z. Also acts on this binary cubic form in exactly the same way. So if you change this basis omega theta by an element of GL2Z, then the binary cubic form also transforms in exactly that way. So that's why this is a well-defined association. Makes sense? By same element. So how is this discovered? What Dillon and Fedde did, they wrote down a general multiplication table for a cubic ring, right? They could assume that these two coefficients are 0, right? And then they noticed that the associative law forces these 3 structure coefficients to be determined by these 4, right? And then they examined, well, what happens to these 4 coefficients when you change the basis? And they found that these A, B, C, D transform just like they would transform if they were the coefficients of a binary cubic form. And so that's what led them to guess that cubic rings are parametrized by binary cubic forms. So given a ring structure, you get a binary cubic form, and conversely, given a binary cubic form, oh my gosh. Woohoo. All right. So given a binary cubic form, you can form a cubic ring by just taking your A, B, C, D and making this multiplication table. So form R using this star. And that's a right star and this star star here. Right? And that's going to be a cubic ring. Right? So given a cubic ring, you just take these 4 coefficients and you make your binary cubic form, and given a binary cubic form, you just make a ring with those being those 4 coefficients, and everything else is determined by the associative law. Okay, so that's what proves the theorem. So it's very explicit for cubic rings. You just look at the multiplication structure using a basis, and you find that these 4 things determine everything, and they behave like a binary cubic form under change of basis. Any questions about the cubic case? Does that make sense? Okay, so we've proven this theorem. Now, in some sense, this was a little too explicit. It didn't sort of tell you what happened. It just sort of works. Okay, so what is really going on here? That's what I want to come to. So, for example, what is the meaning of this binary cubic form? It's a binary cubic form, so it should be a cubic function somewhere on something. So the question is, what is the meaning of this binary cubic form? This binary cubic form, because it was a little bit too explicit. Yeah. Uh-huh. Oh, I see. Yeah, so the question is, we went straight to binary cubic forms, but there's also the issue of binary quadratic forms. And binary quadratic forms are well known to correspond to quadratic rings. And so a natural extension might be binary cubic forms for cubic rings. But there's one thing that's very different about it, which is that binary quadratic forms not only correspond to quadratic rings, but they also correspond to an ideal class. Whereas for binary cubic forms are really in bijection with just the cubic rings, and not with necessarily any ideal structure. So that's kind of a surprise, right? That the ideal classes disappear. So for binary cubic forms, they just correspond to cubic rings. That's the bijection. Okay, so I want to give another interpretation of this Dillon Faddeev correspondence. In terms of what I call resolvent rings. So resolvent rings. So in the classical theory of solving the cubic equation, how does one solve a cubic equation? One reduces it to a quadratic equation, which we already knew how to solve. That's what happens in the classical theory. And what does that mean in terms of field theory? If you have a cubic field, then inside the Galois closure of that cubic field, if it's a generic cubic field, the Galois closure will be an S3 field. And inside the S3 field, there will be what's a quadratic field, right, called the quadratic resolvent field, or the discriminant field, right? So I want to do the same thing on the level of rings. So given a cubic ring R, we can naturally associate a quadratic ring. Can associate a quadratic ring S. How do you do that? Well, R has a discriminant, right? And it's well known that a discriminant is always going to be a number that's 0, 1, mod 4. Okay? But remember, quadratic rings are parametrized by numbers that are 0, 1, mod 4. So given any cubic ring, you can take its discriminant, and then you take the unique quadratic ring that has that discriminant. Okay? So it can, as follows. So that's called the quadratic resolvent. So what's the quadratic resolvent? So the quadratic resolvent of the cubic ring R is the unique quadratic ring such that the discriminant of S is the discriminant of R. Right, so R is any cubic ring, you take its discriminant, and the quadratic resolvent is the quadratic ring that has that discriminant. Okay. We know that such quadratic ring will exist by the parametrization of quadratic rings we gave. Okay, so that's what I mean by a quadratic resolvent. Sometimes we'll call it the quadratic resolvent ring. right? So quadratic resolvent is a ring. It's a quadratic ring. Okay, so to any R cubic, we can associate a quadratic S, right, in this way. And not only that, there's a natural map, actually, from R to S. So in the case that R is, say, an order in a cubic field, this is easier to understand, but you can make sense of it in general. So there's a natural map. Let's call it phi, from R to S. It's not a linear map. Given by sending x, so phi of x. You send it to, remember how we made a quadratic ring of discriminant d? We took d plus square root of d divided by 2. Right, so here, if we're taking phi of x, what we can do is we can take the discriminant of x plus the square root of discriminant of x. Right, d plus square root of d divided by 2. Right, so this can naturally be interpreted to be inside S, right, for x and r. Because a square root of d, square root of the discriminant, is involved. The discriminant of an element is always going to be a square multiple of the discriminant of the ring, so this will actually end up in S, if you think about it. What do I mean by discriminant of x? I should just say, so if we're talking about, so if R is an order in an S3 field, I'll just make it precise in that case. And let x and r have conjugates inside that S3 field. So sorry, this is an S3 cubic field. Let x and r have, so x is going to have 3 conjugates, right, in the Galois closure. Say x prime, x double prime. Then the discriminant of x is defined, well, actually defined, let's just define the square root of the discriminant of x. It's defined to be just the product of the pairwise differences of the conjugates. So we say x minus x prime, x minus x double prime, x prime minus x double prime. Right, product of the pairwise differences. Okay, so if R is an order in a cubic field, we can define a map from R to its quadratic resolvent ring that has the same discriminant just by sending every element to d plus square root of d over 2, where d is the discriminant of that element. Okay, fine like this. And that naturally lands inside the quadratic resolvent. Yeah, you don't. So you pick one, and you do it consistently. For example, if you just use this formula every time, then it'll be consistent. I might have switched these two, and then you get a different map. That would be the conjugate map. When it's not a... Right, yeah, no, then I was sliding it under the rug. But there is a way to always do it consistently. Yeah, so that's why I'm assuming R is an order in a S3 field. You have to be more careful in general, but there is a way to do it consistently in general.
But I mean, X, you're assuming it has 3 distinct conjugates.
So some of the conjugates will, if you lie in the base field, your conjugates will be the same. Yeah. So if you're 0, then all the 3 conjugates are 0.
But then the discriminant is 0.
That's right. Yeah. 0 maps to 0.
But then the square root of 0 is still
it's still 0. Yeah, that's right. Yeah. That's right. Yeah, this will be 0 if x is 0. Right. Right. So yeah, that's right. So if you're in Z, right, then your x is going to x prime, x double prime will all be the same. If you're in Z, if x is in Z, then this is always 0. So Z is mapping entirely to 0. That's right. Which actually brings me to my next point. So, okay, so this is a natural map. It's not a linear map, but it's a natural map from R to S. So maybe. So this map has two important properties. So phi has two properties that I want to note. First of all, phi preserves discriminants. In other words, the product of the pairwise differences of x, of the conjugates of x, are going to be the product of the pairwise differences of the conjugates of this, viewed as a quadratic thing. So that's something you can check. So that's something that seems to play a role in these parametrization of rings everywhere. The fact that you look for maps that preserve discriminant. So you start with something in a cubic ring, it's discriminant. You go to a quadratic ring, the discriminant there, when you map it, turns out to be the same. So that's sort of a recurring theme that we'll see later. But the more important thing I want to note is that phi actually descends to a map. Phi bar from R mod Z to S. Right? Because the point is, if you translate x by something in Z, right, this side doesn't change. That doesn't change. Right? If you translate x by something in Z, right, that's what you were just asking. If you're in Z, you map to 0. And in particular, if x is translated by something in Z, it doesn't change its phi of x. So phi bar is actually well defined on R mod Z. And so I can even do that. So phi descends to a map from R mod Z to S mod Z. Okay, so what's the point here is that, well, as a Z module, R mod Z just looks like Z2, right? And S mod Z looks like Z as a Z module, right? Because this is a cubic ring and this is a quadratic ring. And since we're looking mod Z, this part is not really mattering. It's only this that's mattering, and this is a cubic map. Right? So as a map from R mod Z to S mod Z, this is a cubic map. So phi gives a cubic map from R mod Z to S mod Z. In other words, phi gives a cubic map from Z2 to Z. And what's a cubic map from Z2 to Z? That's a binary cubic form. So phi bar is a binary cubic form. And in fact, it is exactly the binary cubic form that corresponds to R under the theorem 3 that we wrote before. So under the Stillone-Faddeev-Gann-Gross-7 correspondence. So phi bar is the binary cubic form. And it's the same one as in theorem 3. So this sort of gives a ring theoretic sort of interpretation of that binary cubic form. It gives a meaning. That binary cubic form represents a fundamental map from a cubic ring to its quadratic resolvent ring. Namely, this map, square root of discriminant, essentially. Okay, it's this cubic map that preserves discriminants from a cubic ring to its quadratic resolvent. So that's sort of a ring theoretic interpretation of that binary cubic form. Okay, so there are two reasons I wanted to talk about this. First is that, first of all, it gives a meaning to that binary cubic form, which before was just as part of a correspondence. But secondly, this perspective actually helps to go beyond n equals 3. So n equals 3 was sort of the last case that was understood for a long time. The reason being that if you try to solve n equals 4 in the same way, by writing a general basis, writing down all the multiplication coefficients, and then looking for some pattern, looking for some set of coefficients that will determine everything else, it doesn't work in the case n equals 4. Because there is actually no set of coefficients that are independent that determine everything else, once n is at least 4. So that method of Dillon and Faddeev that worked for n equals 3 doesn't work for n equals 4. And so you need a new perspective. And so this sort of gives a new ring theoretic perspective, and this is actually something that allows one to continue beyond n equals 3. So maybe I'll just start by stating the theorem for n equals 4. And then I'll talk about n equals 4 in more detail next time. But just to say, how does one continue this perspective? So why did we think of the quadratic resolvent in the first place? The quadratic resolvent comes up because it sort of comes as a natural way to solve the cubic. You go through the quadratic. In the classical theory of solving the quartic, how does one solve the quartic? One goes through the cubic resolvent. Okay. So when you have, say, an S4 quartic field, if you take its Galois closure, you get an S4 field of degree 24. And if you take the fixed field of the dihedral group, you get a cubic field. That's called the cubic resolvent field. And so in order to parameterize quartic rings, we can try to go through that cubic field by developing an integral theory of this cubic resolvent. So we want to make a cubic resolvent ring for a quartic ring. That's sort of the key to go to n equals 4. So given a quartic ring, so a quartic ring means a ring of rank 4, so let's call it Q. To try to parameterize such Qs, we want to find a cubic ring R of the same discriminant and a map, say phi, we'll call it phi again, from Q to R that first of all preserves discriminants. Okay, that would be the analog of what we just did in the cubic case. Right? So instead of now doing a quadratic resolvent, we're going to call this a cubic resolvent. So does such a map exist from Q to R that preserves discriminants in this way? So there is actually such a map that's used plenty. That's used a lot in the classical literature in solving the quartic. So I'll just tell you what that is. So such a map exists from theory of solving quartic. It's defined as follows. So let's assume, so say Q is an order in an S4 quartic field. And let X and Q have conjugates in this Galois closure of this S4 quartic field. Let's call them X, X prime, X double prime, X triple prime. Okay, then what's the natural way of taking X, X prime, X double prime, X triple prime, these set of conjugates of a quartic element? What's a natural way of sending it into a cubic field? You can do it as follows. So then phi is given by, so you take phi of X, find it to be X, X prime, plus X double prime, X triple prime. So if X is an element of a quartic field, then this thing is going to be an element of a cubic field, right? Because if you let S4 act on this, you're going to get three other things, right? Namely X, X double prime plus X prime, X triple prime, right? And X, X triple prime plus X prime, X double prime, right? Right, so this thing has three conjugates, right? So this naturally takes a quartic thing and sends it to a cubic thing. And so here's the thing I want you to check before the next lecture, is that this preserves discriminants. So this is a really fun calculation, which everyone should do at least once in their life. So what does it mean to preserve discriminants? That means that if you take the product of the pairwise differences of the conjugates of X, that's equal to the product of the pairwise differences of the conjugates of phi of X. Okay, those turn out to be exactly the same. That's a polynomial identity, just like in the quadratic case. So check this, and this will be the key to understanding the parametrization of quartic rings next time. Okay. Okay, thanks. Are there questions? I don't know. Do we do questions?